So today we're moving into 12.6. Which is focusing on circular and periodic functions. Now, part of what we are doing today is actually going to look very familiar because it's really building off of what we've already been doing. We've already been working with our unit circle. Unit circle, by definition, again, is a circle of radius 1. And our unit circle, one of the biggest advantages is it allows us to evaluate things. We can evaluate things such as sine of pi over 3. To do this, again, remember what we do is we pull up that unit circle, we find the angle being pi over 3, and on the unit circle, sine is the y values. At pi over 3, the y value is the square root of 3 over 2. So, sine of pi over 3, square root of 3 over 2. We can also do our reciprocal functions and angles that are not necessarily directly on the unit circle. If they're not directly on the unit circle, what I mean is they're too big or too small to be on the unit circle, during which we find a coterminal angle. And remember, a coterminal angle is an angle that varies by a full circle. Since this is negative, it's too small, so I'm going to add a full circle, which is 360 degrees. 360 degrees plus that negative 210 is 150, and so I'm just going to do secant of 150 degrees. Go to my unit circle. 150 degrees is in the second quadrant. Now, secant is also not directly on here, but secant's a reciprocal of cosine, and cosine's the x value. So, the reciprocal of negative square root of 3 over 2 is 2 over negative square root of 3. Now I pull that negative out front, and I rationalize my denominator by multiplying both the top and the bottom by the square root of 3. I get 2 square roots of 3 over 3. So this should, in theory, look familiar. Now it gets a little more complicated again when we do things like tangent. Of, for example, tangent of 5 pi over 6. Because 5 pi over 6 being right here is really easy to do, but because tangent isn't directly on here, tangent is sine divided by cosine, which these should be down at the bottom of your unit circle. And sine divided by cosine means y divided by x. So 1/2 divided by negative square root of 3 over 2. So 1/2 divided by negative square root of 3 over 2. To divide fractions, I flip the second guy and multiply, keep change. Flip, multiply by the reciprocal is technically what it's called. Multiply straight across, keeping in mind my positives and negatives. Positive times negative is negative. 2 over 2 root 3. And I simplify my fraction. So I get negative 1 over root 3. And don't forget to rationalize the denominator. In the end, I end up with a negative square root of 3 over 3. So far, all of this should look familiar. if I ask you to evaluate a trig of an angle, finding the exact value of that, you are going to be looking at the unit circle. Some questions are going to look a little different, though. Some questions are going to say something along the lines of the terminal side of an angle in standard position. Intersects the unit circle at the following point. Find sine of theta and cosine of theta. Now, there are multiple ways that I can approach a problem like this. Overall, there's the easy way and there's the hard way. Right now, I'm giving you a coordinate point. And if I'm giving you a coordinate point and asking you to find the trig ratios, you can always go and graph your coordinate point. 4/5, -3/5 is down here. Draw my triangle to the nearest x-axis. Label my x, label my y. Don't actually write this down. If you've already started writing it down, my bad. I should have said that sooner. But you can go through and you can do this and you can find the radius and all that wonderfulness. But let me save you some work. The radius is going to be 1. How do I know that? Because this is the point that it intersects the unit circle. And the unit circle is a circle by definition of radius 1. So the hypotenuse of my triangle is going to be 1. In fact, I wouldn't do this at all. If you already did it, it's not the end of the world. Just leave it there. This is a coordinate point on the unit circle. Is it on the unit circle that we can see on this? No. But there are a lot of points here that we can't see. There's one here and here and here and here. Don't draw these. Here and 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 here. And that's just between 0 and 30 degrees. You get the point? There's a lot of them. There are an infinite number of points on this circle. We just labeled the important ones. Now, just because it's not one of the important points on the unit circle doesn't change the fact that on the unit circle, sine is the y value, cosine is the x value. So if I want sine of theta, just look at the y value. Sine of theta is equal to -3/5. Done. Cosine of theta is the x value. Cosine of theta is equal to 4/5. Done. If I give you a coordinate point and tell you that that coordinate point is on the unit circle, I do not care if you can find it on the unit circle or not. It's there, which means sine is the y value, cosine is the x value. The one thing you have to make sure that you are doing when I do this, though, is something you have to make sure that you are doing every single time you come across fractions. Can I leave a fraction as -2/8? No. Simplify your fraction. -1/4. We're good. Cosine's the x value. X value is square root of 15/4. Can we leave something as square root of 15/4? Well, 15 doesn't divide by any perfect squares, but it's in the top of the fraction, so we're good. So far, I hope we're doing okay. There's more that we have to talk about today. So this, so far, is this idea of circular functions. It's working with that unit circle. But we also have this idea of what are known as periodic functions. Periodic functions are functions, shocking, I know, whose y values repeat after a specific interval. To be periodic is something that's not specific to math. Things happening periodically happen repeatedly after specific intervals. Now, when it comes to periodic functions, we have what is known as a period and what is known as a cycle. A period is the length of time of the interval, specifically, that a function takes to repeat. It's how long it is that a function takes to get back to where it started and start again. A cycle is that full repeat. It's that full repetition of the function. For example, if we think about the seasons as being periodic functions, the period is the length of a year, 365 days, because it takes 365 days. Okay, take a little bit with the spring equinox and fall equinox and winter equinox and all that, but that's not the point. Let's just call it 365 days would be the period for seasons to repeat themselves, and a cycle would be the full repetition, would be the year. Calendar works the same way. The period for a calendar, it takes 365 days for it to start repeating. That's the period piece. And the cycle is the year itself, is the 2024 or 2023, whatever year you're talking about. So, the other thing you're going to be asked to do today is to find the period of a function. And the way that you're going to be asked to do this is you're going to be given a graph. Now, periodic functions go on forever and just repeat and repeat and repeat and repeat, which means since the y values are what is repeating, the x is going to keep going on forever, and the y's are going to stay within a certain range. Now, what that range is going to vary from problem to problem. So I'm going to have this graph here. It's going to have a really long x-axis. Y-axis is going to be kind of squat. And that's Okay, now the graph itself. Graph's going to start on the here a little bit underneath the 4. Darn Notability, I didn't want a straight line. It's going to hit there. Then it's going to loop up and do this. Then it's going to loop up and hit between the 12 and the 16. Then it's going to loop up and hit that 20. Then it's going to loop up. And at the end, I'm not really going to see where it ends. But it keeps going. It keeps going in this direction as well. I want to find the length of the period is technically what I'm looking for. So how long it takes for it to repeat itself. Now be careful, some of these are going to be easier than others. Now to find a full repeat, the easiest thing to do is find a good starting place where you can easily see exactly what number it hits. So in this case, that means like the X, where it hits the Y-axis, is not actually helpful. Because I can't tell exactly what number it's hitting. But I can tell where it hits the X-axis. Generally, things you want to look for is where it hits the X-axis, also known as zeros, or high points or low points. Now, the high points here are not the easiest either, so I probably wouldn't use them. This one I would use where it hits the X-axis. Now, it hits it a number of times. I pick a starting point. And then I say, okay, how long until it starts to repeat itself fully? Now, it could start here, but the question is, does it? Sometimes yes, sometimes no. In this case, it does start to repeat itself. So you can go from here to here. And the question is, what's the distance there? Well, this place is at 2. This place is at 8. The distance between 2 and 8 is 6. If you didn't know that, it's 8 minus 2. Big minus little. That's the period. That's what you do here. Now, some of these are going to be a little harder to work with than others. So we're going to do just a couple more examples. Sorry, don't mind me just pausing for a second. Okay, anyway. Okay, so some of them are going to be a little more challenging than others. Because if you look at ones like this, it's not exactly obvious on where it's hitting the X-axis. It's not obvious where it's hitting its high points and where it's hitting its low points. Now, on this one, I'm going to tell you right now, assume that I can draw things accurately the same. All of these U's are supposed to look essentially the same. So sometimes you also might have to read between the lines. You might notice that on this graph, it looks like the graph is getting closer and closer to certain values, but never actually hitting them. In other words, it looks almost as if there's an asymptote here. Lean into that information. It looks almost as if there's an asymptote here. It looks almost as if there's an asymptote here. Generally, if it looks like there's one, there probably is one, and you can use that information. So I can use that information to say, okay, I need a starting point and an ending point. I generally am going to start as far left as I can. Okay, I started at an asymptote. I need to end at an asymptote. But does it end at this asymptote? Is this a full cycle? And the answer is no. Because for that to be a full cycle, that would mean that between every asymptote, my graph would need to look like this. No, it's not what it looks like. So be careful of this. I'm going to start here, but I'm going to go all the way to here until I start getting something repeating itself. Because now it says my graph needs to do this and this in every repeat. Hey, guess what? It started doing that. So, I need to figure out the location of these little markings I've made. Now, if you look here, my scale appears to be counting by 4 on every tick mark. That means this is -4. And this one is 28. The distance between -4 and 28 is not 24. When you have negatives involved, be careful. Always just do big minus little. And remember that when you subtract a negative, it ends up adding. And 28 plus 4 is 32. I got one final example for y'all. Some of the graphs just get a little more challenging because they start to do things like put things in radians. The process is the same. Oops, I'm going to try that again. I'm going to try to just make it a little smoother. I'm not erasing anything. So, when it comes to ones like this, again, we're looking for easy things to find. High points, low points, or x-intercepts. Now, we've been doing x-intercepts, or at least we did on the first one, but those x-intercepts are unlabeled, and high points and low points are easier to see on this one, so I would choose one of those. Personally, I would choose the high points. Here's why. This high point is located at an x value of 0. It's really easy to subtract with 0. The next high point is here. The next high point I can't see, but the question is if I start here and end here, is that a full repeat of the graph? After I get past, does it start doing the same thing? It started up top, looped down, looped back up. back up to the top, looped down, looped back up. Yes, that's a full repeat. This is 0. This is 3 pi. 3 pi minus 0 is 3 pi. If you had done the x-intercepts, you would have gotten the same thing. The only thing is there, you'd have to be careful, first off, to make sure you get a full period going from here to, say, here. And then you'd have to figure out these values. To divide 3 pi over 2.5, to get this one, you get 3 pi over 4. And these are counting by 3/4. I should choose a non-highlighter to write in. This would be 3 pi over 4. So that's 3/4. Technically, the 3/2 is 6/4. This one is 9/4. The next one is technically 12/4, which simplifies to 3. This one's 15/4. You have to know how to work with your fractions to get from 15 pi over 4 to 3 pi over 4. Actually, I said that backwards. You'd subtract, you'd get 12 pi over 4, which is 3 pi. So you can do it this way, but there are easier ways. Okay, homework assignment for tomorrow. I mean, today for you guys. Sorry, I'm recording this the day before. I don't remember what it is off the top of my head. Page 833, numbers 3, 4, 6 through 18, 20 through 25. Overall, a pretty easy day of stuff in my own opinion. I think you will do just fine. Be amazing for the sub.